All right, buffers. Buffers are probably one of the more important features of this chapter when it comes to the human body, because this is our ability to deal with medicine, to deal with food. So you can imagine that everything we eat has some kind of pH, whether it's acidic or basic, depends on, if it's sour, if it's bitter, so to speak. But everything is going to be not neutral. So your body's job in the stomach is to acidify it and break it down. But then very quickly, as it goes around in the bloodstream, we want to maintain that 7.34 or so kind of pH. And in order for that to happen, we're going to have to be able to buffer all of those incoming amino acids and proteins and sugars and carbohydrates and lipids and so forth, because they're all going to adjust the pH, and our ability to maintain pH is exactly what a buffer's job is supposed to do. So maintain pH form, conjugate pairs, is really what we're after. So how can we recognize an acid in its conjugate base? How can we recognize a base in its conjugate acid? Well, the easiest way to think about both these definitions, because they do show up in the matching as well as a couple other questions. If you're an acid and you're going to the conjugate base, you're going to be losing H+. When that happens, you're also going to gain a negative charge. So you can imagine that when you're a base and you're going to a conjugate acid, you're going to be gaining H+. And then as a result, depending on your base, if it's neutral, you might, you have two choices really. If you're neutral, you're going to be gaining a positive charge. And if you're negative, you might be gaining a neutral charge. But really the major difference is, are you losing a hydrogen because acids are proton donors, or are you gaining a hydrogen because bases are proton acceptors? So here's a list of some common buffers. Acetic acid's a great one, and that's because it's weak. You'll notice that in order to be a buffer, you have to be weak. And the reason that you have to be weak is you have to be ready and waiting with a hydrogen to be removed or a hydrogen to be accepted, so that when you eat food, you can neutralize it. If you're a strong acid or a strong base trying to be a buffer, as soon as you go into water, as soon as you go into the bloodstream, you're going to lose all your acidity or all your basicity all at once. And if you lose all that acidity or all those hydrogens, if you gain all those hydrogens very quickly, then there's going to be no ability to lose or gain when you eat food or when you take medicine, and that's not what we want. So really the definition of pH-based buffers is twofold. We want to maintain or resist pH changes. So maintain pH, resist pH changes, same idea. And we have to be weak. If we're strong, we're going to get rid of our hydrogens and gain our hydrogens too quickly, whether we're acids or bases, doesn't matter. So you have to be weak and you have to maintain pH. So acetic acid is organic, so it's very weak, and it has that hydrogen ready and waiting for medicine like Tylenol to bring in its amine to get neutralized. Carbonic acid is the acid system, or the acid-base buffering system of our bloodstream, because we can turn oxygen into carbon dioxide, and it can dissolve into water to make carbonic acid, much like the atmosphere to make rain acidic. Hydrofluoric acid, not too useful. It's strong enough to etch glass, so not too useful for us in the human body. Ammonium, ammonia, those kinds of things can take place in, say, the urine. Phosphoric acid, very similar as well. And then hypochlorous acid, more useful in, say, pools and spas than anywhere else. So in this conjugate pairability, again, it's this loss of H+, gain of H+ issue that we're after. Imagine that conjugate pairs are just like two sharks floating around in your bloodstream, just like floating around or swimming around in the ocean. Their job is to eat these little fish, these little acids and bases. So the red shark represents acid, so its job is to eat these little basic fish or these hydroxides. And the blue shark is acetate, which its job is to gobble up all the protons, which is hydronium and water. And as long as you have enough of those sharks in the ocean, your body maintains a pH of around 7.3 or so. The problem is all drugs and all food, it's everything in moderation, right? There's a reason you can only take so many milligrams of a drug in a certain time period. That's because of the buffering capability of your bloodstream, among other things, but that's one of the majors. So you can imagine if you take loratadine, which is Claritin, or if you're smoking, or if you're drinking caffeine, taking a bunch of morphine, or if you're taking a bunch of meth. The reality is all of those have amines, and amines are basic. So they're just like hydroxide, just a little bit weaker. But either way, these red sharks, these acid sharks, the acid of your bloodstream has to neutralize those medicines, those foods, in order to keep your body stable at that 7.3 kind of range. The more base you take, the more it's going to want to push you to a high pH. So from 7.3 to say 8 to 8.5 and beyond. But because we have these buffering sharks based on carbonic acid, not based on the acetic acid shown in the picture, we have the ability to maintain pH as long as we're taking one pill or two pills every several hours or so forth. So you can imagine that an overdose is really just the ability to take too much that your body can't handle. So too much meth just means your pH goes from 7.3. The first little bit of meth you take would be a little bit of basicity, but your sharks can handle that little bit of basicity. But if you just keep taking meth, one shot after shot, or however you take meth, I don't know. There's lots of different ways. But regardless, even with say lots of shots of espresso, or a whole package of Claritin because your allergies are going crazy, one pill's fine. A couple cup of coffees is fine. But too much is going to put your body into a coma, whether it's a food coma, whether it's a real coma. It's all based on this concept. If you have base coming in, we only have the ability to neutralize so much so fast. So if you keep dumping base in, your pH is going to go from a 7.3 to an 8, and you're going to get sleepy. If it continues to get too basic, your body is going to start shutting down, and it's going to say, the only way I know to keep you safe is to put you to sleep, not knowing that all these pills are still dissolving in your bloodstream, or all this meth is running around in your veins. It doesn't know it maybe until it's too late. So as your pH goes to closer to 9, you go into a coma. If nobody finds you, you die. And that's where overdoses come into play. Medicines that are too basic, have too many amines, they can shift that balance too far, and your pH gets too high, your organs can't survive, your brain tries to save you by putting you to sleep, and then you fall asleep. Same thing's true for Thanksgiving. When you eat a lot of turkey, you're eating a lot of protein. It's a lot of bases from those amino acids, and just a lot of food in general. So you're basically really putting those sharks to a test because you're eating more food than you ever have, all year long. So there's lots of theories about tryptophan and so forth, but the reality is you just shifted your pH beyond control, so your body puts you to sleep so that it can catch up. So those food comas are a lot related to real comas, and they're just a way for your body's buffering capability to maintain itself. They know that if you're asleep, you can't eat another piece of cake or another piece of turkey. And if you're also asleep, you can't take more pills, even though your body can't realize that you've already taken 10 or 15. And that's an issue if nobody finds you. So you can imagine taking something that is too acidic is also just as bad, because you can kill all those blue sharks, all those base sharks. So a lot of aspirins, Tylenols, ibuprofens, vitamin C's, if you take too much of those, they're too acidic because they have carboxylic acid groups. So taking one aspirin can help, whether it's inflammation or thin your blood or whatever. But if you take a whole bottle, you're going to kill all these blue sharks. You're going to now push your pH from 7.3 down to maybe a 6.3. You fall asleep, you get tired. And then if it goes much further than that, you go into a coma. And if nobody finds you, it goes further than that and you die. So it's very important to realize that the reason for dosages over a certain amount of time is all because of acid-base chemistry. It's all because of this buffering system of our blood, and it can only do so much. So as we look at any kind of conjugate base, think about those definitions we mentioned. They're giving us an acid, and we said in order to find a conjugate base, just get rid of H+. Once you do that, all you really have is C5H7O6. None of that changes, but now we have O negative. Because if we lose H plus, because we're an acid or a proton donor, because we lost positive, that negative is still going to be there. Those electrons from that hydrogen atom still there. And that's what we're after for a conjugate base. Just remove or lose H plus. If you want an acid, then just add H plus, and that's the simplest way to think about it. So pay attention to those H's, no different than any of the other videos of this chapter. As we look at a buffer specifically, we have to worry about its ability to be weak, and this one does have carbons and it is weak, so it could be a buffer. We also need to have its conjugate base, and if you take away H plus, you do get carbonate, the ion with a -2 charge. So if you have hydronium, just remember hydronium is acid. So this is basically acid plus water. And if we're an acid, we have to realize which of the sharks could we regenerate. Well, if we use the carbonate shark and add H plus, notice we're going to get hydrogen carbonate, the anion. And you can imagine that with OH negative down at the bottom, very similar but different. This is base, and the only hydrogen that is available is this one. So if we use the hydrogen carbonate shark to attack this one, we're going to produce water, which is neutral, but also we're going to produce carbonate because now this hydrogen would be gone because it's now present in water. It's no different than over here. If we take away H plus, notice we formed water in the process. So either way, we're maintaining pH. We're resisting pH changes, and we're also using a weak acid or base to do it. So again, just pay attention to that H. Pay attention to where it goes. We want to make sure that we're regenerating the other shark. It's the circle of life in your bloodstream. If you're killing off all your sharks, that circle of life stops. And if we're not reforming the other shark at the expense of one shark, then we're also not doing our body any favors because those one sharks will run out eventually if we take too much medicine or eat too much food. And that's the reality of acid bases in the body. So real quick, I want to show you just a representation of what you can think about with a lot of the ions that we've seen before and how they kind of fit themselves together back in chapter 2. So you can imagine that if we have something like hydrogen phosphate, that its ability to have a conjugate base of phosphate is all acid-base chemistry. It also has the ability to come from dihydrogen phosphate. And it has the ability to come from phosphoric acid. So this ability to donate H pluses is the ability to be an acid. So you can imagine then if the ability to be an acid is to donate H plus, we have 3 to donate, we have 2 to donate, we have 1 to donate. That's what it means to be a triprotic acid in the end. So as you give H plus to somebody else, as you give H plus to somebody else, as you give H plus to somebody else, that's what it means to be an acid. Notice PO4 doesn't have any H's, so it can't be an acid at all. The opposite is also true, that in order to be a base, you have to accept H pluses. So if you have an H plus and you accept it, you're going to become HPO4 -2. If you're a base and you accept hydrogens, you can work in the opposite way. So the ability to lose and gain hydrogens is important for any molecule, not just the ones in our human body. But the ability to gain H's is really based on the ability to have negative charge, whether that negative charge is visible, or even if we were to write Na3PO4, these are just parking spaces for hydrogen atoms. So this gives phosphate the ability to be a base, But notice it has no hydrogen, so it can't be a acid, so this is a base only. HPO4 negative 2 is an acid because it has an H, but it also has 2 parking spaces for more hydrogen, so it can also be a base. H2PO4, which is dihydrogen phosphate, has 1 parking space left. It can be a base. But notice that H3PO4 doesn't have any room left, right? There's no charge, no spaces left. And that's why we call it phosphoric acid, because it's an acid only. So its ability to be a proton donor is the ability to be an acid. And its ability down below to be a H plus acceptor is the ability to be a base. And when we were learning all these ions for the first time back in week 5, this is what we were after. It was just, we haven't gotten to the acid-base chapter enough to understand why it was important or why it needed to happen. You can also imagine that the acids and bases, conjugate acids, conjugate bases, if you're an acid only, then as you move over, this would be your conjugate base. If you're a acid only, if you move over, this can be your conjugate base. If you're a acid already, you can move over and be a conjugate base. The reverse is also true. If you're a base only, you can accept a hydrogen and be a conjugate acid. If you're a base, you can become a conjugate acid by accepting H+. And if you're a base, you can accept hydrogens and become conjugate acids. So both of those ideas are true. So pay attention to, are you donating H+, or are you accepting H+? And you can figure out conjugate acids, conjugate bases. But you can also figure out why all these ions work together with hydrogen back in those earlier chapters. Next chapter is electron transfer. So we'll catch you then.